In this video, we will solve through the problems from homework 2. These problems are basically about 2's complement arithmetic, IEEE floating point number representation, preventing arithmetic overflows in our programs, and finally some simple truth tables. So let's get started here. So here we are given two 8-bit 2's complement numbers, and we basically have to add them and figure out whether there is any overflow. So let's do this here. This is the first number. The second number is 0 0 0. There are 4 zeros followed by 1 0 1 0. So let's perform this addition. 0 plus 0 is 0. 1 plus 1 is 1 0, so 1 goes over carry. 1 plus 1 is again 1 0. 1 goes over carry. This is again 1 0. 1 plus 1 is 1 0. This is 1 0. Again 1 0 and 1 0. So this is the final answer. Now notice that there is no overflow here, because if we focus on the sign bit here, right, this is the sign bit, the carry into the sign bit is exactly the same as the carry out, and therefore there is no overflow. You can also double check this by converting these numbers into decimal. So this actually is the first number is -10, and the second number is +10. So -10 plus 10 is equal to 0, and there is no overflow. So here we have to subtract two 2's complement numbers. So recall that a minus b is the same as a plus minus of b. So essentially we have to first compute 2's complement of the second operand here, and then add it to the first operand. So first do that. So 2's complement of this number is, let's flip the bits, so all the ones basically become zeros. Then forget about the first number and add a 1 to the flipped version. So this is our number. So this is basically 1. So now we can add this 2's complement to the first operand. So we have 1 0 0 0 0 0 1 0. We have to add it with 1. So let's do that. So this is 1 1 0 0 0 0 0 1, right? And once again you see there is no overflow, because you see by default the carry in was 0 and the carry out is also 0, so there is no overflow here. So this is the answer. This is another straightforward addition. So let's do this here. You have 0 1 1 1 1 1 1 1, and the second number is all ones. So essentially this is 127 plus minus of 1. So we add them. 1 plus 1 is 1 0. 1 goes over carry. 1 plus 1 plus 1 is 1 1. So 1 goes over carry. Once again this is 1 1 1 1 1 1 1 1 1 1. This is 1 0, so 1 goes out carry. Now notice that this if we focus on this sign bit, right, the carry in was 1 and the carry out is 1, and therefore there is again no overflow here. So this is the final answer. This question is basically asking us to do minus 128 minus of 128. Okay, so both of these are negative 128. Now recall that the 8-bit 2's complement range is minus 128 to plus 127, and therefore this negative or 2's complement of minus 128, which is 128, is out of this range. Okay, so to do this correctly, we should first extend both these operands to 9-bit representation instead of 8-bit. Okay, so after the sign extension, this minus 128 basically in 9 bits would be 1 1 followed by 7 zeros. Okay, now once again we use the same trick that a minus b is the same as a plus minus of b. So to compute minus of b, we should compute 2's complement of this number. So once again flip the bits, so zeros becomes ones and ones become zeros, and then forget about the original number and to the second number here, add a 1. So we get 1 plus 1, 1, 0. This is again 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. Right? So this is your answer. This is positive 1. So this is 1, 0, and this 0 should also come down. Right? So this is 9-bit representation. So this is positive 128. Now let's just add this to negative 128. We should also extend this first operand into 9 bits. So do a sign extension because this is a negative number, so that becomes basically 1 1 followed by 7 zeros, and this second number is copied from here, so we have 0 1 followed by 7 zeros. Let's add these numbers, so we get 0 plus 0 0 0 0, this is 0 0, this is again 0, 1 plus 1 is 1 0, 1 goes over carry, 1 plus 1 is 1 0, 1 goes out. Right, so we can ignore this carry out because once again notice that this was the sign bit after the sign extension, so the carry into the sign bit is the same as the carry out, and therefore there is no overflow. This is your final answer. So obviously minus 128 minus of 128 would be minus 128 plus 128, which is 0. Right, so because 0 is in this range of 8-bit 2's complement numbers, there is no overflow here. Okay, there is no overflow in this case either. So this problem is asking us to translate 69.625 into IEEE floating point representation. So the first step is to convert 69.625 into binary. Okay, so we'll basically convert 69 into binary. So for that, let's use this long division method. So go on dividing by 2 and keep track of the remainders, right? So here we get this goes 34 times, the remainder is 1. Let's keep going. This goes 17 times. The remainder of 0, this goes 8 times with the remainder of 1. Similarly 4 times, this goes 2 times, this goes once, and this finally goes 0 times with the remainder of 1. Right, so read this bottom up. This is your 69. So 69 is basically 1 0 0 0 1 0 1. Right, now we need to convert 0.625 into binary. So recall that every position in binary digits, you will recall that this every position after the binary point represents a power of 2. Right, so this is to the power negative power of 2, actually to the power minus 1, this is to the power minus 2, this is to the power minus 3, and so forth. Right, so basically 0.625 can be written as 0.5 plus 0.125. Right, so notice that this is 0.5 is to the power minus 1 and 0.125 is to the power minus 3. Right, so basically 0.625 is 1. If you just mark a 1 to in these at these powers of 2 after the floating point, then you should get the binary equivalent of 0.625. Right, so this is 101. So essentially this number 69.625 is in binary is 1000101.101. Okay, now from here we need to translate this into IEEE floating point representation. Let's do that on the next slide. So we are translating 69.625 into floating point representation. So we have seen that this is the same as 1000101.101. okay, so now the next step is to convert this binary representation into scientific representation. Right, so basically we need to move this floating point to the left. So this number basically becomes 1.000101 multiplied by 2 to the power. Now you see we have moved this floating point 1 2 3 4 5 6 positions to the left, so this should be multiplied by 2 to the power 6. Okay, so the next step is to basically figure out the sign bit, the exponent bits, and the fraction part. Okay, now recall that the sign bit is just 1 bit, exponent takes 8 bits, and fraction takes 23 bits. Okay, so the sign is positive, this is a positive number, so the sign bit would be simply 0. The exponent is 6, but recall that exponent 6 would be represented as this should be represented in excess 127 notation. right? So the way we do that is we first translate 6 into 2's complement, which is basically in 8 bits would simply be 0 0 0 0 0 1 1 0. Okay, and now just add 127 to this. So 127 is basically 0 1 1 1 1 1 1 1. Just add this and we get the excess 127 representation for 6. So this is 1 plus 1 is 1 0. This is 1 plus 1 plus 1 is 1 1. Again this is 1 0 1 0 1 0. This is 1, right? So this is 6 in excess 127. So we have 1 followed by 4 zeros followed by 1 0 1. Okay, and finally the fraction, recall that it only stores the binary string that follows after this decimal point or this binary point, right? This 1 point, right, this is always assumed or implied because we are always converting the binary representation of the decimal number into scientific representation, and therefore the fraction here would store simply 0 0 0 1 0 1 1 0 1, and then we have to pad it with enough zeros so that the total number of bits here is 23. So this is 9 bits, so we have to pad it with 14 zeros to the right. So this becomes let's do that here. This is 23 bits. Let's put all of these together, right? So one after the other, and come up with the hexadecimal representation. So the first bit here is the sign bit followed by the exponent, which is 1 0 0 0 0 1 0 1, followed by this string over here. So we have 0 0 0 1 0 1 1 0 1 0 0, and then we have 12 more zeros. Let's translate this into hexadecimal. So make groups of 4 starting from the right. Okay, so this is 0, this is 0 0 0 0 0 in hexadecimal is 0, 1 0 0 is 4, 1 0 1 1 is B, 1 triple 0 is 8, this is 1 0 2, and this is 4. So our answer is hexadecimal 428B4000. This is our, so this is basically the IEEE floating point representation for 69.625. In the second part, we need to convert minus 123.75 into IEEE floating point representation. So once again, we'll first translate 123 into binary, and then we'll translate 0.75 into binary, and then we'll do the conversion or representation. So let's start with that. So let's use the long division method to convert 123. Go on dividing by 2 and keep track of the remainders. So this goes 61 times remainder of 1, 30 times with the remainder of 1, 15 times with the remainder of 0, 7 times with the remainder of 1, 3 times with the remainder of 1, 1 time with the remainder of 1, and then 0 times with the remainder of 1, right? Now read this bottom up. So 123 is basically 1111 Now what about 0.75? So again, recall that every position here is a power of 2, negative power. This is to the power minus 1, to the power minus 2, to the power minus 3, and so forth, right? So 0.75 is basically 0.5 plus 0.25, which is basically 2 to the power minus 1 plus 2 to the power minus 2, right? So this should be 1 and 1 at to the power minus 1 and to the power minus 2. So 0.75 is 0.11, and therefore minus 123.75 is basically minus of 1111011.11. Alright, so let's now finish this on the next slide. So we are translating minus 123.75 into IEEE floating point representation, and so far we have seen that this in binary is basically minus of 1111 011.11. So the next thing we should do is we should translate this into a scientific notation. So once again, so we need to move this decimal point 1 2 3 4 5 6 positions to the left, so this would become 1.111 01111 into 2 to the power 6. Next we need to determine the sign bit, the exponent bits, and the fraction bits. Again, this is 1 bit, exponent is 8 bits, and the fraction is 23 bits, right? So because this is a negative number, the sign would simply be 1. So sign bit is 1. The exponent right now is 6. So 6 in 2's complement is basically 000000110. But we need to further translate this into excess 127 notation. So we do that here. Just add 127 to this bit pattern. So we get 00000110, adding 127, which is 0111111. We simply get the excess 127 notation. So this is 0 plus 1 1. This is 1 0. This is 1 1 1 0 1 0 0. This is 1, right? So this is our answer. So in the excess 127 notation, this is 100000101. Okay, and the fraction, again recall that we assume that this initial part is implied, so we only need this and then pad it with enough zeros so that everything counts to 23 bits. So the fraction is basically 1110111. This is 8 bits, so we need 15 more zeros. Alright, so this is 23 bits. So let's put these together. Let's put this and this together to get the final answer. Okay, so the final answer should be in the form of hexadecimal representation. So let's make groups of 4 starting from the right. This is 0, this is 0, this is 0, this is so 1 triple 0 in hexadecimal is 8. 0 triple 1 is 7. All ones is basically F, right? 4 ones is F, 1 0 is 2, and 1 1 0 0 is C, right? So our final answer minus 123.75 in hexadecimal is IEEE floating point representation is basically C2F 78000. The problem number 3 is now asking us to do the other way around conversion. So we are given numbers in IEEE floating point representation, and we have to determine the corresponding decimal numbers. So the first step should always be in such problems to translate the given string, the given hexadecimal string, into binary. So our string here is hexadecimal C1BE0000. C is basically 1100, 1 is 0001, B is 1011, E is 1110, and then these are 16. These will translate to 16 zeros. Okay, now from the IEEE floating point representation, this 1 bit, this is the sign bit. The next 8 bits, these are the exponent, and the last 23 bits, this is the fraction. So the sign bit is 1. This means our number is a negative number. The exponent is 1 followed by 5 zeros and then 1 1. So this is in excess 127 representation. We need to translate this back into decimal, and then this is the fraction. So let's work on this on the next slide. Alright, so far we have seen that the sign bit is 1, the exponent is basically 1 followed by 5 zeros followed by 1 1, and the fraction field is basically 0 1 1 1 1 1 followed by several zeros. Okay, so let's translate this exponent, which is right now in the excess by 27 notation. Let's translate this into 2's complement. So to do that, we need to add this exponent to minus 127, right? So we have 1 0 0 0 0 0 1 1. Minus 127 is basically given by 1 followed by 6 zeros followed by 1, right? So let's just add these two numbers. So we get 1 plus 1 is 1 0, 1 plus 1 is again 1 0, this is 1 0 0 0 0, 1 plus 1 is 1 0, right? We can discard this overflow carry, and basically this is our exponent. So this is basically 1 0 0, and in decimal this 100 is basically 4, right? So this is the exponent. The fraction, recall, it does not store the leading 1 before the decimal point, right? So there is an implied 1 point before this fraction. So essentially our number is, the number that we are looking for is basically it's the sign bit is 1, so it's a negative number. The after adding this 1 point, the fraction becomes, or the significand becomes 1.011111 multiplied by 2 to the power 4. Okay, so once we multiply this binary point will move 4 positions to the right, so it should come here. So this is our number, negative 1.11. Now we just need to translate this into decimal. So just as we have seen, every position here is a power of 2, right? So this is to the power 0, this is to the power 1, this is 2 square, this is 2 cube, and this is 2 to the power 4. Similarly, every power after this decimal point is a negative power of 2 every position. So this is to the power minus 1 to the power minus 2. Let's add all of these. So the number basically becomes negative of 2 to the power 4 is 16 plus, so this will become 0. So let's add 4, 2 square, then 2 to the power 1 is 2 plus 2 to the power 0 is 1 plus 2 to the power minus 1 is 0 0.5 and 2 to the power minus 2 is 0.25, right? So let's do the math here. So all of this comes to basically minus 23.75. So as we can see, this was the original answer. Part 3b is actually asking us to translate this hexadecimal number into decimal. So once again the same procedure. Let's first translate this given hexadecimal number into binary string. So 4 is basically 0 1 0 0. Basically every hexadecimal digit translates into 4 binary digits, right? So 2 is basically 0 0 1 0, C is 1 1 0 0, 6 is 0 1 0, I'm sorry, 0 1 1 0, 8 is 1 0 0 0, and then this would be 12 zeros. So basically each zero will translate to 4 zeros, so this is going to be 12 zeros. So from the IEEE floating point format, this is the sign bit followed by 8 bits of exponent and followed by 23 bits of fraction. So the sign bit is 0. What that means is our number is a positive number. Let's continue this on the next slide. So far we have the sign bit is 0, the exponent is given by 1 0 0 0 0 1 0 1, and the fraction is basically 1 0 0 0 1 1 0 1, and then followed by a bunch of zeros. Okay, so let's so sign is 0. What that means is this is a positive number. Let's now, this exponent right now is in excess 127 notation, so let's first translate this into 2's complement number by adding minus 127 to it. So we have 100000101. Let's add minus 127, which is basically 1 followed by 6 zeros to get the 2's complement representation. So 1 plus 1 is 1 0. This is 1 1 0 0 0 0. 1 plus 1 is 1 0. We can discard this overflow carry, right? So the exponent is basically 110, which in decimal is 6. This is our exponent. The fraction, once again recall that the fraction has an implied 1 point before it. Okay, so our number is, it's 1.10001101 multiplied by 2 to the power 6. So let's do the math here. So after multiplication, this will move 1 2 3 4 5 6 positions to the right. So our number would be 110011.01. We just now need to convert this into decimal. So once again, powers of 2, this is to the power 0, to the power 1 is 2 square, 2 cube, to the power 4 is to the power 5, to the power 6, right? And once again, these are negative powers. To the power minus 1, this is to the power minus 2. Let's add all the powers that are corresponding to ones. So the number becomes 2 to the power 6 is 64 plus 2 to the power 5 is 32 plus, so this will be 0, this will become 0, this also becomes 0. 2 to the power 1 is 2 plus 2 to the power 0 is 1, and after the decimal point we have just 2 to the power minus 2, which is 0.25, 1 by 4. So let's add all of these together. So all of this adds up to basically 99.25. So this is our final answer here. The fourth problem here is about avoiding overflow in arithmetic computations. So we are given three integer variables a, b and c of C++, and we want to do c into a into b. Obviously this computation may result in an overflow if a and b are large integers, such that the product does not fit in the integer range of this language. So the question is asking us to come up with a code that does this, computes this product but avoids the overflow. Now this is a very similar idea to what we have seen in class in with respect to adding integers. So this is also included in slide 23 in lecture2.pdf on Canvas. Let's assume that a, b and c are three integers in C++. Let's assume that int max represents the largest integer that can be represented in C++. So the largest integer that can be multiplied with a without causing an overflow is given by int max divided by a. So before computing this product a into b, we should first check whether b is greater than this max multiplier. If so, then this product will definitely cause an overflow, and therefore we should report some error over here. If not, if b is less than this max multiplier, then we can safely compute the product. So this is the basic idea in this solution. Question number 5 is asking us to compute the truth table for this function. The function is true only when exactly one of these two conditions is true. If both the conditions are true, then the output is 0. If none of the conditions are true, then also the output is 0. The output would be 1 if exactly one of these two conditions is true, right? So condition 1 here is x is false, which means the value of x should be 0. And condition number 2 here, the second condition is saying that exactly one of y and z is true, right? So either y should be 1 or z should be 1. So these are the two conditions. Now let's walk through this table to figure out the values. So the first row is 0 0 0. So x is false, and so the first condition is true, but both y and z are false. So the second condition is not true, and therefore exactly one of these two conditions is true. Therefore the output should be 1. In the next row we have 0 0 1. So x is false, so the first condition is true, uh, and z is 1 but y is 0, right? So exactly one of y and z is true, so which means even the second condition is true, so both the conditions are true, and therefore the output should be 0 here. The third row is 0 1 0, so again x is 0, so the first condition is true, and y is 1 and z is 0, so again exactly one of y and z is 1, so this is also true, so basically both the conditions are true, and therefore the output of this function should be 0. The fourth row here is 0 1 1, so x is 0, so the first condition is again true, and now both y and z are true, so basically the second condition is not true, so basically exactly one of them is true, so the output can be 1. Now in the fifth row here we have x equal to 1, so the first condition is false, and y and z both are 0, so so the second condition is also false, so the output would be 0. Next we have 1 0 1, so x is true, so basically first condition is false, and z is 1 but y is 0, so the second condition is true, so basically the output can be 1. Next we have 1 1 0, so x is true, again first condition is false, and only y is true, z is 0, so the second condition is true, so what that means is the output can be 1. The last row has all ones, so the first condition is false and the second condition is also false, because both y and z are true, therefore the output should be 0. This question is asking us to compute the truth table for a function which is true only if there are two or more ones among the four inputs, right? So out of these four inputs a b c and d, there should be at least two ones, two or more. So in the first row here, the number of ones in the input is 0, because all the inputs are zeros, and therefore the output should be 0. In the second row here, the number of ones is exactly 1, and therefore this is less than 2, so again the output is 0. In the third row, we have exactly 1 1, all other three inputs are 0, so again the output is 0. Then the next row we have two ones in the input, and therefore the output can be 1. After this we again have just one in the input, just one in the input, all others are 0, therefore the output is 0. After this we have two ones in the input, so again the output is 1. Here we again have two ones, so the output is 1. Here we have three ones, so the output can again be 1. 1 0 0 0, only one in the input, only one in the input, so the output is 0. After this we have two ones, so the output can be 1. Here we have 1 2 ones, so again the output can be 1. Here we have 1 2 3 ones, so the output can be 1. Here again 2 ones, so the output is 1 2 3 ones, so the output can be 1 1 2 3 ones, so again the output can be 1. And here we have all four ones, so the output can be 1. Alright, so this brings us to an end of this discussion. I hope this helps. Please let me know if you have any questions. Thank you.